Topic 11.4 has to do with resolution, and we're going to thank Mr. S for this delightful background that's going to make our foray into resolution that much easier to follow along. And so let's start by talking about diffraction. You remember that if you have light traveling through a thin slit, that if we go through here and we imagine there's a thin slit here, that light develops some diffraction pattern, a series of bright and dark lines because of the diffraction as the light spreads through beyond that slit. Well, the same thing happens because if you think about it, our eyeballs are essentially slits. Light enters them, and when it enters them, it actually diffracts, and so you get diffraction patterns on the backs of your eyes. And what happens, or what can happen, is if two sources of light are too close together, the diffraction patterns basically overlap each other and you can't distinguish between the two objects. When we talk about resolving objects, we're talking about whether or not you can tell that they're actually two objects. So if I were to draw a blue dot here and a blue dot here, I'm going to assume that you can see those two blue dots. You were able to resolve those two blue dots. Now, if you were to leave your device that you're watching this on right now propped up against the wall and slowly back away, at some point you're going to get to the point where you can see, you backed up and so you couldn't hear what I was saying, but now that you're closer you can probably hear me again, so that's good. But while you had backed away, you probably at some point got to where you could not tell, or you could not distinguish between the two blue dots, and perhaps it looked something like this. One large dot. As you're backing up, maybe there was a point where you could kind of see, and it looked like this. Okay? So these are different levels of resolution. Here we have something that's fully resolved. Here you have where you're not able to resolve the two points at all. And that point where they're still well resolved occurs when the primary maxima of the two sources, I'll call this source 1 and source 2, when those two maxima are separated, you can resolve the two objects. But what happens is as you back away, as you get further away, those two maxima, because the angular separation actually decreases, or the actual, as you're backing away, the apparent distance between them decreases because you're further away, and so they seem like they're closer. As you get further away, those maxima get closer and closer together until at some point they overlap. And when they overlap, when those maxima overlap, as they do in this image here, you can't resolve the two sources. You get something like this. You get a single object. Well, just before that point, you get what's basically the minimum allowable separation, where you can still distinguish that there are two sources. And so if you look at this here, you're just able to tell that there are two sources. That's the minimum separation at which you can resolve them, and that's what we call the Rayleigh criterion. And the Rayleigh criterion is that minimum angular separation that any two objects can have and still be resolved. Now, if we remember from let's see. Now, this Rayleigh criterion says that if the central maxima, so the brightest maxima, the primary maxima for one diffraction pattern, coincides with the first minima of the other diffraction pattern, then the two sources will just be resolved. And so, if the one maxima basically lines up with the minima or the dark spot of the other diffraction pattern, then you're going to be able to resolve the two objects. And so, as you can see in this picture, then the angular separation is half the angular width of one central maxima. And in this equation, B is going to be the slit width. So that angle is lambda over B. And up until this point, all of the optical slits that we've talked about have been rectangular, right? They've been just our general slit. When we're talking about your eye or something like a microscope or a telescope, the aperture is a circle. And for round apertures, the formula is a little bit different. You don't necessarily need to know the derivation of it, but it's going to be 1.22 times lambda divided by B, where again B is the diameter of the aperture. And here lambda is called it's basically the minimum angle of resolution. It's the minimum angular separation that two objects have to be resolved. And this is what we call the resolving power. If we look at the human eye, the diameter of the pupil, or the average diameter of a pupil of a human eye, is about 2.5 millimeters. And so if we have 2 points of orange light, let's see if I can pull up some orange here. There we go. So 2 orange dots have to have an angular separation of 2.4 times 10 to the negative fourth radians in order to be resolved. Okay, and that angle we're talking about is this angle here. And so let's set this up. Here's your eyeball. So here's our 2 orange dots. In order for your eye to resolve these 2 dots, this angle here has to be 2 times 10 to the negative fourth radians. Okay, so obviously we're talking about angular separation, and what that means then is for 2 objects to be resolved, their actual distance apart as they get further away from you has to increase in order for them to be resolved. And so that's why if you have 2 dots on a wall, when you're up really close, you can resolve them. You can see that there are 2 dots, but as you get further and further away, it becomes harder and harder to distinguish between the 2 dots. And this also comes into play when we use, as we mentioned, both telescopes and microscopes as we try and look at things that are very, very far away and things that are very, very small. Your typical radio telescope is about 25 meters in diameter. And the reason for this is because of the wavelength of radio waves. Because of the longer wavelength, if we were trying to, if the human eye could observe or could see radio waves, our pupils would have to be roughly 600 meters to actually resolve two sources of radio waves. And so this is why radio telescopes have to be so big. And what they often do is they'll actually put them, they'll have two of them, and they'll have them further away. They'll have them separated by some distance, and that'll allow kind of the same effect. They'll allow them to resolve the two objects. And as I mentioned, you get the same effect when we're using microscopes, whether it's a light microscope, electron microscope. You still have this issue of resolution and of having objects that need to be a certain distance apart in order to resolve them. Now obviously with the microscope we can resolve things that are smaller, but even with the microscopes there's still a limit to the resolving power. For microscopes, we actually have a slightly different equation that we can use, and again, D, where D is our resolving power, is equal to lambda over 2m. And in this equation, m is it's a property of a lens. It's a constant for a lens, and it's called the numerical aperture. And that's really all you need to know about that at this point. But if you look at this equation, what you should notice is that the smaller the wavelength, we actually have a better resolving power, because as the wavelength decreases, the distance between the two that's required to resolve them decreases. And with our electron microscopes, the wave nature of our electrons tells us that they have a related wavelength of about 5 times 10 to the negative 12 meters, which means that with our electron microscopes we can resolve objects that are a quarter of a nanometer apart, and so very, very small objects that are very close together. Now, some typical problems that you're going to get related to this, you might have to figure out how far away cars must be from your eyes before you can resolve the headlights. And this is one where you can maybe think about it as you might see cars way down the highway. You're driving on the highway and oncoming headlights looks like it's one headlight, or you just see one light, and as it gets closer and closer and closer, you're slowly able to tell that there are actually two headlights instead of just one. And so you might have to calculate the distance when that actually happens. When we're looking at other types of problems, when you're talking about telescopes, they might ask you to find the diameter of a telescope required to resolve two binary stars, and it would give you, given distances and angles and things like that. So those are the kinds of things you'll have to try and solve for using your knowledge of resolution.